Welcome to the walkthrough for worksheet 10 question 4. This is the last question of the worksheet, which means your mentor might not have reached here. But this question is a proof of the Pythagorean theorem, which you can see from the question title. It's Pythagorean pain. Anyways, let's move on to part A of the question. Let us now explore an application of projection with the following setup. Suppose we have points A, B, which have the coordinate as listed, as points in the first quadrant in the 2D plane. Then suppose O is the origin 0, 0, and C lies at the point on OB and is closest to A. What is the relationship between OA, OC, AC? So, immediately from entering the prompt, we notice a problem. There's too much information. So, usually when we face a geometrical proof like this, or algebraic, and encounter too much information, one way to simplify the solution of a problem is to first try to figure out the setup of this proof. Or in other words, try to draw a picture that represents what the proof is trying to prove. So that is precisely what part A tells us to do. Let's say that there's this point A, which is A comma B, and another point B, which is C comma D. And once again, I have another point O, which is the origin of my coordinate plane. Know that A and B are both in the first quadrant. So OA is going to be drawn as the line segment between O and A. OB is the line segment drawn between O and B. And it would be a little more helpful if I shift A a little to the left, because I will have to draw a point that is C, where C is the point on OB that is closest to A. Okay, relationship between OA, OC, and AC we'll talk about later. For this part, we're just going to draw out a setup of the proof. But we can probably notice some kind of hint here. For example, C is the point on OB that is closest to A. This tells us that OC is the closest vector to OA that is in the direction of OB. This will remind you of a special algebraic thing that we talked about in the last question, and that is called the projection. In other words, OC is equal to the projection of OA onto OB. We will come back and use this fact later. This fact is also not part of part A solution. I am just mentioning it here so that I can refer back to it later, now that I have realized there's this piece of information I might be able to use. So now let's move on to part B, which it asks us to express the length of OA in terms of an inner product. You can define any vector you use in this inner product definition in terms of A, B, C, and D, which are the components of the vectors before. Let us remind ourselves that OA is this vector that goes from point O, which is 0, 0, to A, which is A, B. The length of OA is equal to the magnitude of this vector OA, and we can express the magnitude of a vector by using the square root of its inner product with itself. Where we also notice that the vector that goes from O to A is equal to the vector of A minus 0, B minus 0, and that is precisely vector containing the components A, B. So if you end up solving the entire expression of the length of OA, you'll notice that it's equal to square root of A squared plus B squared. But since the question demands us to write length of OA as in terms of an inner product, we'll stick with this solution that I circle here. So that was part B. Now let's move on to part C. Express a vector that has a same direction and magnitude as OC. Same direction and magnitude. Well, let's review the setup of our question again. I have this setup that I show you on the left side of the screen that we just drew in part A. I'm going to copy it to below part C so I can reference it later with you. So once again, notice that OC is in the direction of OB because, as we have said before, OC is equal to the projection of OA onto OB. So OC is once again in the direction of OB. So it's a scalar multiple of OB to be a little more specific. Okay, so now we just have to find the projection of OA onto OB to settle with this. Remember that the projection of some vector x onto y is equal to x dot y over y dot y times y itself. So projection of OA onto OB would be, by the way, this is the definition. We didn't derive this. We didn't derive this or come up with this just now. We did not make up our sources. To see the derivation of projection identity, you can check the walkthrough video of the last question. So coming back to this, projection of OA onto OB is equal then to OA dot OB over OB dot OB times OB. Now we just have to write this in terms of components. The dot product of OA and OB. Well, once again, OB is going to be equal to the vector going from 0, 0 to CD. So OB is equal to CD. CD what? CD as in CD the components that we have stated before in the prompt. And once again, OA is AB. So the dot product is AC plus BD, and the magnitude of OB squared, which is the inner product with itself, is C squared plus D squared, and OB is CD. Yes, CD. Okay. So I'm gonna try to shrink the window, which my finger cannot. Here we go. So now that we have expressed a vector that has the same direction and magnitude as OC, we can now express the length of AC in terms of ABCD, which is what part D does. Okay, and just to mention again, we know that OC is a projection of OA onto OB by the reasoning that we have discussed when we're talking about part A. So in other words, we should immediately notice that, first of all, OA is equal to OC plus CA, or OC plus AC, if that's what you want to say. So the length of AC is equal to the vector that goes from point A to point C. But finding out the exact coordinate of C is painful. We have already done that, but to compute AC's length based on that is very painful. So we would rather actually first try to find an expression of AC so that we can deal with the length later. So that's one way of solving the problem. In this case, I see that AC is equal to OA minus OC. Or actually, more accurately, OC is equal to the vector from C to A is equal to the vector from O to A minus the vector from O to C. You can see that because CA is the vector going from C to A. Summing up OC and CA on the left side of the screen leads me to the vector OA. This forms a triangle. I do know OA. OA is just AB. Meanwhile, OC is, well, we've written the expression of OC somewhere before, which is in part C solution, AC plus BD, over C squared plus D squared CD. I'll stop explaining the solution of part D at here because usually an exam is not insane enough to tell you to express the length of this vector, which would actually just require you to state the magnitude of the vector that I write below here. That is just summing the two vectors together. Like, normally people would not want you to express the length of this vector directly. That is pretty insane. So we'll stop at the expression of CA. And if you wonder about the length of this vector, it is actually just square root of the sum of squares of the component. And for video length reasons, I will not be expanding the notation. Last but not least, in part E, using previous subparts, prove that line segments OA, OC, AC follow the Pythagorean theorem. What is probably your first reaction to this, because how does OA, OC, AC relate to Pythagorean theorem at all? Well, this is where we borrow the power of part A, which is to set up the problem with a geometrical image, so that we can see how exactly might they obey the Pythagorean theorem. So I'm going to copy the set from part C to part E. There's a very important point here, which is that OC is equal to the projection of OA onto OB. And what this tells us is that OA minus OC, which is actually equal to CA, is perpendicular to OB. The difference of a vector with itself, the difference of a vector with its projection is perpendicular to the direction upon which it's projected onto. CA is, in other words, perpendicular to OB. There's another way you can know this. C is the closest point on OB to A. So, in other words, C is where... So, in other words, if A has a shortest distance between itself and OB, C is where the shortest distance when written as a line segment will extend onto. The shortest distance expressed as a line segment will always be perpendicular to the original line that we're finding a distance from. So OB must be perpendicular to AC. Okay, now I'm going to draw this picture a little more precisely. So in other words, we're going to try to prove, now that we have a right triangle here, that OC squared plus AC squared is equal to OA squared. So one way out of this is using algebraic notation. There's another way to answer this without mathematical expression, which is just to say that triangle OAC is a right triangle due to projection property that we have described before. And this projection property, or the property of projection vector, is that the projection of the difference between OA and the projection of OA onto OB must be perpendicular to OB itself. The reason for this we have also addressed in the previous part of the question. So you can directly say this, and that will form a good solution to the problem, because you may answer without mathematical expression. But if you answer with mathematical expression, here's how we'll do it. First of all, notice that OC squared is equal to, well, we have written this expression before, right? It is equal to the dot product of OC with itself, where we see that OC is equal to this very complicated expression, AC plus BD over C squared plus D squared is CD. AC is even more complicated. The dot product identity stays the same, but AC is equal to AB minus OC. And that is slightly annoying, because we have to then expand out a whole lot of things. So here's where I plug in a trick called substitution. I'm going to call M is equal to AC plus BD over C squared plus D squared. So that in every computation that follows from here, I'm going to abbreviate these numbers as M. So in other words, OC becomes M times CD, AC becomes A minus CM, B minus DM. OC squared, or the length of the square length of OC, is then equal to C squared M squared plus D squared M squared. AC squared is equal to A minus CM squared plus B minus DM squared. So that's equal to A squared plus B squared minus 2ADM minus 2BCM plus C squared M squared plus D squared M squared. Now I'm going to add these two values up, such that OC squared plus AC squared is equal to A squared plus B squared plus 2 times c squared plus d squared times m squared minus 2 ad plus bc times m. Okay, now let's substitute back m and see what happens to the equation, since we have simplified the equation to a sufficient amount. So m is equal to ac plus bd over c squared plus d squared. So 1 of the c squared plus actually let me write out the FOILed out expression first, and then explain how we go about simplifying the fraction. C squared plus d squared. Alright, so now that we have figured out these details, what we can then do is we can try to simplify the expression. First of all, a squared plus b squared here doesn't change. The c squared d squared cancels out, so we have 2ac plus bd over c squared plus d squared minus 2 ad plus bc, ac plus bd, c squared plus d squared. Okay, so now what we then do here is that we try to... Actually, there's one thing I forgot to put here. So let's continue off where we left off. Footage recording issue, I don't know why. So, we left off here, but forgot a couple of things when I was recording the passage. First of all, this AC plus BD should be squared. And second of all, this is actually minus 2 ACM and minus 2 BDM. So that was a algebraic error. Which means we actually have AC plus BD as a product here, as our coefficient here instead of AD plus BC. So we actually end up with the following expression where we're subtracting 2 times AC plus BD squared over C squared plus D squared with the same thing. And these terms zero out. So in the end, I end up with A squared plus B squared. And that I got as OA squared according to the Pythagorean theorem, which would hold true. So then we are able to prove that OA, OC, and AC do follow the Pythagorean theorem. So last but not least, I will stop the video, stop some frames of the video at the screenshot of my total solution. And have a nice day.